Twarog to our front and center. Yeah, Cam's project was Alaska Remote Microgrid Power System Simulations, and his mentor was Mari Shirazi. So yeah, we'll welcome Cam to the stage.
Thanks, Jeff. You got my name perfectly. All right. So, oh, great. I just want to see how the remote works. Okay, great. All right, so I'm Cam Twarog, and I was working with Mari this summer on modeling some infrastructure upgrades in the Northwest Arctic Borough in the villages of Shungnak, Ambler, and Kobuk. This picture is of Ambler near one of the mining districts out there. And so first we'll talk about some background in the region and the project, and then we'll start talking about the goals for what I was researching, and then talk about some results and lessons learned that I would take forward with work in Alaska. So Shungnak, Ambler, and Kobuk are these three small villages. There are a few hundred people each in like the southwest area of the Brooks Range. And yeah, they're in the Northwest Arctic Borough. They're really cold. They're like they're a little bit colder than Fairbanks. But the thing that's interesting about these villages, and that's a real challenge, is that fuel is extremely expensive, and the cost of energy in these three villages is some of the highest in all of the state, and which already has really high prices. I think they're looking at like, I don't know, like prices in the range of 50 to 60 to 70 cents a kilowatt hour, which is really high. And that's due to the heating fuel and the diesel oil needing to be flown in on planes. The river, the Kobuk River that flows near all these villages is shifting course and becoming more shallow, so they can't really barge in fuel anymore. And I think heating oil right now is $14 a gallon in Kobuk, which is very expensive. And so there's a few infrastructure upgrades that are being explored in this region. One of them being oh, you can't see Ambler on the map. Wait, maybe. Okay, so right now there's a interconnect, an electrical transmission line between Shungnak and Kobuk, but there is some exploration and research being done in building a medium voltage DC interconnect between Ambler and Shungnak. And that's kind of a novel technology that is being explored due to reduced costs and other reasons why it would be useful in remote Arctic regions. Ease of construction on like tundra and permafrost being another really big reason. So Nathan Green and Michaela Chamberlain and Mari have been doing a lot of good work on this MVDC. And so I was assuming we are going to build that MVDC. Now we're going to look at this new hydroelectric site on the Kogaluktuk River. And there's been some good studies done about 10 years ago on this project. And so, but there hasn't been any modeling of the entire region and what the future of energy could look like in this region. So I was doing some modeling in Homer to model this site. As you can see here, this is the site of the intake for the hydro. It'd be a run of river, so there'd be no dam. The fish could still run in the river. And yeah, so that's kind of the goal would be to turn off diesel generators as much as they can and kind of reduce the reliance on diesel fuel. And yeah, so project goals, as far as ACEP goes, we're gonna look at the technical and economic feasibility of this new hydro project. And we're gonna research potential uses for the excess hydroelectricity. The project that engineers recommend would be oversized for the loads in the community. So we would have extra electricity in the summer months that we need to figure out what to do with. And then also we are going to look at a few different transmission cases between the villages. We're interested in the medium voltage DC transmission lines. So we're gonna look at those versus more traditional AC transmission lines and see price and performance, what would be the best choice. And the bigger goals, the main goal as ACEP's goal is to reduce energy prices in Alaska. And being that they burn so much fuel and the fuel is so expensive in these villages, we wanna reduce that to lower energy costs. And we don't wanna have to rely on these like kind of sporadic fuel fly-ins every few months. And then we also wanna, gain some resilience to fluctuations. As we know, prices to oil are very volatile and can be really challenging for our villages to pay for oil. Okay, so I was using Homer. All of my modeling was in Homer Pro, which a few other people have used. It's similar to Zendy, which Gus was using. And we built out this model, and this model is basically built out by Nathan and Michaela in their previous work on the MVDC. So we are kind of looking at, let's go back. Yeah, we're looking at this big grand scheme to upgrade the energy in the region, which would take all of the diesel generators and remove them from Shungnak and Kobuk and put them all in Ambler. So then fuel can be barged into Ambler. So these are the 3 diesel generators that power the whole region. And then we're going to add in the Kogaluktuk River Hydro, and there's some existing heat pumps, and yeah, so we can input an electric load. And then Homer finds the optimal layout of the electrical system and will tell you how much extra excess electricity you have. Will tell you the cost per kilowatt hour, the total capital cost. Like, there's just so much data you can get from Homer, so it's great. And we want to look at technical and economic aspects of this. And so maybe we'll take some look at quick results from this. So this, if we add the hydro and we can get enough money for the hydro, it's really, really great, because before having the hydro, we need to run the total cumulative generator run hours are almost 13,000 hours per year, meaning we have like 2 or 3 generators running at a time sometimes. But with the hydro, it's only 3,000 hours a year, which means there's like a good half of the year, more than half the year, where there's no diesel running, which is like really wonderful. I feel like I've read reports of like diesel off operation in some of the villages, and it's just like silence, and it's just like really this like magical moment when the diesel generators are off. So that could be really cool. And then fuel costs or fuel burned for electricity is almost cut like an order of magnitude. It's drops from almost 700,000 liters to 79,000. So that's really great. Yeah, we do have to start the generators more frequently due to some like other fluctuations in the electricity sources. But yeah, and then so some of the graphs that I produced. This is the generator output for the villages. So red is the case where we don't have the hydro. It's what exists now. And it would basically just follow the cumulative like demand in the villages. So you can see this is typical in Alaska. Summer demand is way lower than winter demand because there's no space heating really in the summer, and we don't need as much lighting, and there's just way less demand. But in the blue, our generators are like, it's running at like half the capacity. And then there's this whole like long summer through fall when the river's really flowing and we can turn off the generators completely, which is really great. And then this other question we were thinking about was what to do with all the excess electricity that we're not using. And so a huge part of my project was modeling heating loads and heating demands, which is like, seems like one of the big unanswered questions in kind of Alaska and northern energy planning is 75% of energy uses is heating. But a lot of the studies we're doing is just looking at electricity usage. So we're only looking at a quarter of like the total energy consumption. So I was interested in this like bigger picture of reducing overall energy consumption or fossil fuel consumption, because the houses are heated using heating oil, which is just diesel. So yeah, this green line is what I came up with for the residential heating loads. And I did that based off of, I wrote a lot of like Python scripts and did a lot of research on average fuel consumed per household, then used some census data in the villages to like figure out how many households there were, and then got hourly temperature data, and then distributed like this estimated heating oil consumption by temperature. So when it's really cold, we're consuming a lot more diesel in the villages for space heating. But so I just put all this like 2 weeks of work into this, and then we plot it. And this is the hydro excess electricity. It's like nothing compared to the total demand for residential heating. So we kind of started pivoting, and we're like, all right, well, maybe for this 1 month in the summer, we can electrify the homes, but that's like not worth the investment. So yeah, we're now kind of thinking about other long-term storage solutions, like maybe pumped hydro is an option in the hills nearby, or maybe like flow batteries or hydrogen, or like some other long-term storage could be a good alternative. And then also we wanted to look at the economics of the project. And so this red line here is the case where no hydro. And what we're looking at is On the horizontal axis, we have the price. So here we're at $3 a gallon down here, all the way up to like $18 a gallon up here. And then this is the price per kilowatt hour going here. So as our diesel price increases, we have to burn diesel to make electricity. So that means we're going to be paying more because we're burning fuel. As diesel gets more expensive, we pay more money, as you know, when you fill your gas in your car. And then this blue line is the hydro case, assuming we could get half of the project funded by like grants, like maybe infrastructure grants or the state or some sort of external funding. So there's this point at like $6 a gallon for fuel where our hydro project becomes cheaper than our no hydro project, which means that that would be like the attractive option. And $6 a gallon is pretty good, it's pretty reasonable as a guess for fuel price. That's on the low end, definitely. And then the best estimate that we have right now for the total price of the hydro is like 45 to 50 million. And when we do that, the crossover point where it becomes cheaper to install the hydro is around like $12 a gallon, which is maybe a little high, but still, it's possible if they have to fly another fuel. So yeah, it seems with the right funding sources, it could be like a beneficial and feasible project from the economic standpoints. And then we'll talk about some of the challenges in this project so far. Heat loads are the big challenge. Residential heating loads weren't so bad. It definitely took some time to find the right data sources, and it's probably not super, actually my predictions were really in line. Like I could check them and they seemed really in line with like other data sources I could find. So I feel pretty good about my residential assumptions that I had made, but heating oil isn't really metered in households. Like a household will buy 100 gallons or however many gallons, and then they just burn it when they need heat. But we don't know like at what rate they're burning that. So it's really hard from a data perspective to kind of extrapolate from there and make your own model. And then another question was looking at what loads are constant throughout the year versus what loads are not constant. Like heating in your house, you always turn on your heat in the winter, but in the summer you turn it off. So that's not a constant load. It's off in the summer and really high in the winter. But some loads like laundromats, for example, like dryer heat and like heating in your washing machine, that's the same throughout the year because you always need to heat that water. So these are kind of figuring out what sources of heat are important to us that we care about, that we can separate to include in our models is a real challenge. And that kind of ties into how to use these excess electricity. If we're gonna oversize renewable sources and we have all this excess, what do we do with it? In Alaska, there's this huge imbalance with like, we have all this sun in the winter, in the summer, and like endless sunlight, but we don't need any heat and we barely need any energy at all. But in the winter, we need all this energy. So how do you kind of shift that long term is like a really big challenge that there isn't like one size fits all, it seems like. And then kind of working in rural places in general, I think like how do you find good reliable data that isn't super old and is complete? I could find like annual fuel usage from 1980 for Kobuk, and it was like that's not super helpful because like I want it by the hour for 2021. So then I don't know, you kind of have to predict more, and it just gets more and more like inaccurate the more assumptions you make. So that's a real challenge, but I feel like something we can work through. And I learned a lot about Homer Pro. So takeaways from the summer, I got pretty good at the software Homer Pro and kind of interacting with it and taking data out of it and then interfacing it with Python to make nice plots and to kind of like predict trends and whatnot. It was really great and useful, and the software is really powerful. And then I think this thermal load thing is something that I gained a lot of experience with, and I knew nothing about it. Like I didn't realize how big of a deal it was in Alaska, and it's 75% of all energy use. That's a lot of energy. So it was great to kind of get some hands-on experience coming up with data for that. And then also just gaining familiarity with the Northwest Arctic Borough and rural Alaska in general was really like great. Yeah, I feel like I recognize a lot more dots in the map now and like know a lot more about how things work, which is pretty cool. It feels, yeah, it's interesting to me, like seeing how much exists on these small communities that have 200 people, and if you really dive into the weeds, there's like so many papers and so many reports written about every single village in Alaska. And it's just like, there's been a lot of cool work done by a lot of people, which I think is really neat. And yeah, I just want to thank Mari and Nathan and Michaela and Ingemar as well, and anyone else, a bunch of people, Lindy and Andrew and Sweekar all sat in on our weekly meetings and had great ideas. So thanks, everyone. Questions? Yes, cool.
So how did you model the
Microphone.
Oh,
Right.
so there we go. How did you model the heating loads when like there was no readily available data source?
Yeah, heating loads. So there's like a lot of random reports that you can find. I found like CCHRC had found some stuff. They had done some studies on like, they had average monthly or average annual fuel usage for a single family home in Fairbanks, and they are like a multi-family home in Fairbanks. So you could kind of take some of that stuff and then say, okay, Fairbanks has this many hours a year where you need to do heating, but then Kobuk has this many hours a year where you need to heat. So you could kind of scale it up and then distribute it across like the temperature, I guess. So that was one. And then I would take like that number that CCHRC had come up with and then make my estimate and see how much fuel I burned in my estimate, and then compare that to like what the Northwest Arctic Bureau says is the average heating oil consumption in their village. And if like it all turned out to be pretty similar, like once I had scaled and done all the like distribution and stuff, it turned out like, you know, within like 100 or 200 gallons of each other, which was like close. It feels close enough for a good guess. Yeah.
I've got two questions, but I'm going to start with Rich's question, which I want to have you address first before I get in mine in. What are the limitations of Homer? So you got to dive into that pretty deep.
Yeah. Homer, what are the limitations of Homer? Honestly, Homer is really great for what I was trying to do. I think like the big one is transmission lines. You can't model transmission lines because Homer is meant to like model a microgrid that is just like one village, but a core part of this project is modeling the connection of multiple villages. So how there's line losses across, you know, we lose power to heat and whatever across long distances. We have a 25-mile line. So luckily Nathan and Michaela had done a lot of work on their MVDC study before on how to build that into Homer. And it basically just like you have to run like a power flow kind of analysis on and then yeah, it just takes like a little bit of coding and stuff, and then you can make your own artificial losses and import them into Homer. So I think transmission losses are a big limitation, but they're definitely, it's kind of by design, I think, for Homer.
Well, that probably answered my question, but I want to ask it. So you started this thing talking about transmission and MVDC options, and then pivoted to a specific hydro site. So it sounds like you managed to incorporate the transmission system, but you sort of hand waved away just like this is losses, but it kept all three of those villages as part of the microgrid you were supporting?
Yeah, we basically, Nathan and Michaela, they had combined the total loads for the villages and then looked at, they had done the really long MVDC line, and I did it for the shorter MVDCs between the Hydro and Kobuk, and then for Kobuk and Shungnak. Yeah, and you can do some power loss calculations for every hour of the year, and then import that into Homer as just like an additional electric load that needs to be met.
And that power loss per the year is like that's temperature and other dynamics that are.
Yeah,
okay.
yeah, we did it based on like it's like what power is. I don't know. There's a few electrical engineering equations that have three numbers in them, and kind of doing that. We didn't take temperature into account. It was mostly like a load kind of, you know, voltage drop and resistance and inductance calculations.
All right, and my last trap question is you talked about writing a lot of code and doing other stuff. Have you captured that and put it into GitHub for us?
It's not in GitHub, but it's in nice Jupyter notebooks. Nicely organized.
Nicely organized. All right, well, let's get those into GitHub
Okay.
as a dance here. Okay.
Hi, Cam.
Hi.
That was a really great talk. Thank you. I really enjoyed it. It was really well spoken. I had a comment and a question. I'll start with my question. So I thought that a reduction of like 75% of the diesel demand based on hydropower was a pretty significant finding. But I'm wondering how you modeled your electrical output from hydro, because it's still kind of an emerging industry. What data did you use for that?
Yeah, that's a really good question. So luckily for this project, there was a really in-depth feasibility report. They looked at 4 separate hydro sites back in 2013 in the kind of greater Ambler-Shungnak region. And the project I modeled was the one they recommended the most on the Kogaluktuk River. And they had monthly stream flows. They did have data. They had a nice graph on hourly stream flows, but the actual data wasn't really available. The only numbers I could get were the monthly average stream flows. So right now, I just am modeling a monthly average for the stream flows. So my hydro production is kind of blocky. So that is definitely something to look at. But as far as I can tell, there isn't a gauge that's publicly accessible on the Kogaluktuk River right now.
I'd love to see that report. That sounds great.
It's really great. Yeah, it's like 100 pages long.
Yeah, if you could share that, or if that can go in the link with the intern presentations afterwards, like a link to that reference, I'd be curious to see what was done there.
Yeah, sounds good.
And then I guess my other comment was just, this issue has come up at other meetings, but if the diesel load were to be reduced 75%, this came up in another meeting, that there was a comment at a community meeting that, well, the fuel provider is not going to want to bring anything in if they can't make any money off of it. So if you just cut out a bunch of the diesel fuel, I don't know, have you had any conversations yet about what would happen? Because obviously the community really needs heat in the winter. And if it becomes cost prohibitive for anyone to provide fuel to them at all, that's something to consider in this process. That's all.
Yeah, we hadn't actually talked about it. It's a great point. The only thing we had talked about was by turning off diesel generators, you're losing a lot of the waste heat from the generators, which might be used to heat community buildings. And if there's any like future upgrades to the waste heat infrastructure, then this work might kind of nullify those upgrades. But that's a really good point that we hadn't taken into account.
Yeah, great. Well, thank you very much for your presentation. Nice work.